civilization has been around for over 5,000 years, our view of modern cosmology has largely been shaped by discoveries made over only about the last 100 years. It was only in the 1920s that Edwin Hubble showed that there are galaxies outside our own Milky Way galaxy, and then showed that those galaxies are moving away from us proportional to their distance. This implied an expanding universe, exactly as Einstein's theory of general relativity had implied over a decade earlier. If the universe had expanded since the time it was formed, this implied all the energy we could see, including the energy of matter, was tightly packed together in an extremely hot, dense state at the beginning, and had somehow expanded ever since. This was jokingly named Big Bang by Fred Hoyle in 1949. But the Big Bang was a hotly debated topic until the 1960s, when the debate was settled as Penzias and Wilson, two scientists working for Bell Labs, accidentally discovered the cosmic microwave background, or CMB, which is what we would expect to see if the Big Bang actually happened. It's a microwave radiation emanating from all points in the universe when the universe had cooled to about 3,000 Kelvin. It's the leftover embers of the Big Bang. Today the universe is much cooler, about 2.7 Kelvin. Then in the 1970s, the existence of dark matter, which was originally theorized by Fred Zwicky in the 1930s, was confirmed by Vera Rubin. She found that the rotation of stars in the outer rim of nearly all galaxies have about the same speed as the inner stars. It was theorized that this happens because there's a mysterious halo of matter surrounding galaxies that we can't see. That's why it's called dark matter. In the 1980s, the theory of cosmic inflation was developed by Alan Guth, which seemed to solve several mysteries of the early universe. And in the 1990s, two international teams of astronomers found that the expansion of the universe was not slowing down, as would be expected due to gravity, but was actually accelerating. The energy that would cause this acceleration is referred to as dark energy. And we've continued this progress into the 21st century. For example, we have been able to find more evidence supporting these earlier discoveries, as well as make new ones, such as the measurement of gravitational waves. And we've seen a leap forward in the precision of our measurements of fundamental constants. So that is the historical perspective of the progress of cosmology. What I didn't tell you is that the true start of modern cosmology happened even before Hubble's discovery of the vastness of the universe. It began with Einstein's formulation of the theory of general relativity. Pretty much everything in cosmology has its roots in this theory. So what is it? In a nutshell, general relativity treats gravity not as a force, which it had been thought to be since the time of Isaac Newton in the 1600s, but rather as a result of the geometry of space, and shockingly, of time as well. In fact, it introduced the notion that time is intertwined with space and is equally important mathematically. What made general relativity so earth-shattering was that it described how mass and energy could change the underlying space and time itself. And this change is what manifests as gravity. Before this, space and time were considered to be unmoving, unchanging backgrounds on which massive objects were attracted to each other. Einstein showed that it's the change or curvature in the geometry of space and time that causes objects to be attracted to each other. So much of cosmology boils down to solving the famous Einstein field equation of general relativity. Without getting into the math, let me just give you an intuitive feel for this equation. The left side of the equation represents the curvature of space and time, space-time. The right-hand side contains all the matter and energy of the universe. This is all the stuff that makes up you, me, the planets, and everything around us. This equation simply tells us that the makeup of all the mass and energy of the universe creates a curvature in space-time, which we interpret as gravity. And that gravity, in turn, influences the mass and energy. Physicist John Wheeler said it best: space-time tells matter how to move, and matter tells space-time how to curve. All the complexity of general relativity can be summarized in those simple words. So with this, we can simply plug all the information about matter and curvature that we have spent centuries looking at into this equation, solve it, and obtain the equations that explain our universe. And that's essentially modern cosmology in a nutshell. And plugging everything into the equations gives us a model of our universe. And we can then turn back the time to understand how the universe looked in the past. We know our visible universe is expanding. So this means that if we turn back time, it will become smaller and smaller. So at some point, it should be infinitely small. This is called a singularity. Now, many cosmologists don't think that the universe was actually infinitesimally small at the beginning, and that this is likely just a glitch in the limits of our model. Now, you might say, hold on, why should I believe any of this if you're telling me that there is a glitch in the model? That's a valid concern. But since the model makes many predictions about this early time, which we can test even today, we have a ton of evidence that supports the idea that the model works perfectly fine if we ignore the point where the universe is infinitesimally small. So what we can do is turn back time to just before this glitch. At this point, we can say that the universe was incredibly dense and hot, as all of what becomes of the universe we see today was compressed to a very small size. Let's say the size of a swimming pool. Now here you might ask, how can the entire universe fit into the size of a swimming pool? Well, we tend to think that this is impossible because we're used to seeing objects which are composed of atoms and molecules, and these have a distinct size. But you have to remember that the early universe was not composed of any of this. It was composed of only energy. At its core, all matter is simply energy. Mass is equivalent to energy. Even the rest mass of fundamental particles is energy. The early universe was not even composed of fundamental particles. As far as we know, it was all energy, and energy has no size limit. In principle, it could be contained in any volume you choose. The temperature would just be higher at smaller and smaller volumes. So let's start from as far back as we can go and let the history of cosmology unfold. The timeline of the universe can be divided into about 6 stages. The first stage is when the universe started from what is theoretically a singularity, 13.8 billion years ago. The universe was very small here, maybe the size of an atomic nucleus, but there's no consensus on this. Everything we know starts here. This is colloquially referred to as the Big Bang. But you should know that to scientists, the Big Bang is the entire process of how the early universe evolved, not just the beginning. We also have no idea what came before the beginning or what triggered the universe. Stage 2 occurs at about 10 to the negative 36 seconds. There's a sudden expansion from this unimaginably small volume in a process called cosmic inflation. This is when the universe went from the size of an atomic nucleus to perhaps the size of a swimming pool, almost instantaneously, ending at about 10 to the negative 32 seconds. The temperature was on the order of 10 to the 32 Kelvin. We believe cosmic inflation occurred because it explains some mysteries. For example, it explains why the universe is so homogeneous, why it's flat, and why we have large-scale structures in the universe. The quantum fluctuations at the Big Bang would have become fixed after inflation. This pool would contain a lot of energy, moving around in a kind of soup. Although all the building blocks of the universe that is about to come could be found here, everything was massless at this point. That's because the Higgs field had zero potential and had not become massive yet. This changed as the universe continued to expand and get cooler. This is the third stage, or era of particles, which occurred around 10 to the negative 11 seconds. The temperature cooled to 10 to the 18, or 1 quadrillion Kelvin. At this point, the Higgs field also gained a non-zero potential, and when fundamental particles interacted with this potential, they gained rest mass. I have a video on this mechanism if you want to know more details. And as temperatures continued to fall to about 1 trillion Kelvin, the strong force began. Quarks combined into larger particles, but all except protons and neutrons decayed. Neutrons also decayed unless they merged to bind with protons. The fourth stage was the era of nuclei. This happened when the universe was about 3 minutes old. The temperatures dropped to about 1 billion Kelvin. Some protons and all remaining neutrons now combined to form helium nuclei. By the end of this era, the universe consisted of about 75% hydrogen nuclei and 25% helium nuclei, with trace amounts of some other nuclei like lithium. But electrons and protons floated freely because their kinetic energy at these temperatures was too high to allow them to become bound together. This abundance of free electrons prevented the free flow of photons. So the universe remained opaque at this point. This is why we can see no light from this era through our telescopes. This changed in the next stage, which is called recombination, or the era of atoms. But this did not happen until the universe was about 380,000 years old, and the temperatures cooled to about 3,000 Kelvin. Electrons could now combine with protons and helium nuclei to form neutral hydrogen and helium atoms. The observable universe had grown to the size of about 83 million light years at this stage. Since the electrons were now able to be captured by nuclei, they no longer interfered with the free flow of photons. As a result, the universe changed from being opaque to transparent, and this was the first visible light of the universe that can be seen even today. It's a form of radiation that emanates from all points in space, called the cosmic microwave background, or CMB. This light was originally more energetic, but the expansion of the universe has caused this light to stretch, decreasing its energy to the microwave spectrum. At this point, the universe was mainly composed of hydrogen, helium, and a little bit of lithium. So now the question is, how did we get from this to the solar system today? This leads us to the sixth and final stage of cosmology, the era of stars, galaxies, and larger structures. While the universe is generally homogeneous and isotropic, meaning the same everywhere we look, it's not exactly the same. There are minor differences. So for example, when you look at the CMB, its overall temperature appears to be about 2.7 Kelvin everywhere, but our instruments can pick up small temperature differences on the order of microkelvins. This seemingly minor difference makes a huge impact on cosmological scales because these differences provide the seeds for the structure of the universe. All the fluctuations seen on the CMB can be traced to the large-scale structures of the universe, which consists of clusters and filaments consisting of thousands upon thousands of galaxies. But in order to form galaxies, the universe first needed to form stars. This happened initially when gas clouds consisting of hydrogen and helium combined and gravitational pressure increased over time. Eventually, the pressure becomes so large that condensed balls of gas ignite, forming a star, and the dark ages of the universe is over because we have light from stars. Inside a star, hydrogen gases fuse to form helium, releasing energy in the fusion process. Subsequently, helium fuses into lithium, lithium fuses to heavier elements, and so on. Eventually, within the cores of stars, we also get the elements needed for life, such as oxygen, carbon, and nitrogen. These initial stars were much larger than our sun, so they burned brighter and for a shorter time, lasting only about 1 million years. And they ended their life as spectacular supernovae explosions, as the fusion process stopped after the formation of iron in their cores. Fusion stops with iron because atoms heavier than iron require more energy to fuse than the energy released. So stars begin to die at this stage. These supernovae explosions release life-essential atoms into the space, together with other elements of the periodic table. These remnants, combined with remnants from many other supernovae explosions, eventually form second generations of stars. And the supernovae of this generation can form a third generation of stars, and so on. Our sun and solar system are made from the remnants of prior stars. It was formed when a gravitational clump formed somewhere within a cloud of gas or nebula, consisting of prior supernovae explosions. Our sun, after it got heavy enough to fuse hydrogen in its core, began to shine. The leftover debris from the sun's birth, consisting of heavier elements, formed a protoplanetary disk, which accreted over time to form the planets. That's how the Earth was formed. Galaxies are vast collections of such stars. They also contain significant amounts of gas and dust, but these visible forms of matter do not appear to have enough mass to keep most galaxies gravitationally bound together. Scientists believe there's up to 5 times more mass that cannot be seen because it does not emit, absorb, or reflect any light. This is known as dark matter. And scientists believe it played a critical role in the formation of galaxies. They believe that dark matter formed gravitational centers in the early universe, and these centers were gravitational sinks that attracted visible matter. More matter means more gravity, and so these initial dark matter concentrations became the seeds for larger structures such as galaxies and galaxy clusters. When dark matter is inserted into the Big Bang model, the model quite accurately explains the large-scale structures of the universe we see today, 13.8 billion years after the Big Bang. Now you might ask, why do galaxies spin? These galaxies spin due to conservation of angular momentum. This is similar to how a spinning ice skater spins faster as they pull their arms in. In the case of galaxies, gravity is what pulls everything closer together. The rotation is also why galaxies are generally flat. If you take any object and spin it, it will flatten. Because of this, the Earth is not completely spherical either. It is flatter at the poles because it's rotating, but it's so dense that it still keeps a mostly spherical shape, unlike galaxies. The exact details of why we have different galaxy types are not fully known. Now, there is one more critical piece of the puzzle that needs to be mentioned. It is, in fact, something that accounts for more than 2/3 of all the energy we observe in the universe. Remember the cosmological constant I mentioned briefly in Einstein's general relativity equation? That constant is what we can call dark energy. It's like an anti-gravity force that pervades all of space-time. It turns out that it is causing the galaxies and the large-scale objects to move away from each other at an accelerating rate. Thus, everything that is not bound by a sufficiently strong gravitational pull will drift away over time. And the further away it is, the faster it will do so. So one can say that in the early universe, when dark matter dominates and the attractive force of gravity reigns supreme, things got together and formed structures. But as the universe aged, dark energy has become more dominant, which does the opposite and makes things move faster away from each other. And there seems to be nothing that will stop the universe from expanding at an ever-accelerating pace until someday we see nothing except the stars in our own galaxy. But this won't happen for at least another 150 billion years,